it's not the whole story, because the matter doesn't satisfy the Schrödinger equation.
And then there's gravity, which is described by Einstein's theory of general relativity, and that theory doesn't know anything about quantum properties.
It means that it is not only that the future is open, but the past is not fixed.
Now, that doesn't mean string theory is right. It just means it's the only game in town.
Quantum computing suggests that we can go below this level of the particle universe and tap directly into the CPU of the universe.
Let me backtrack a little bit. When I was talking about quantum mechanics, one of the problems is that the theory doesn't really make sense. Some people call it the best theory you've ever had in science. Maybe it is. I don't think it is myself, because it's it's inconsistent with itself. And this is because there's an equation called the Schrödinger equation, which tells you how the quantum state evolves. And it's very deterministic, like Laplace and all these other people. If you know what the state is now, and you know what the things you put into that is to say the matter or whatever it is you're talking about, what's called the Hamiltonian, you feed that in, then the Schrödinger equation gives you a deterministic evolution. If you know what the system is now, then in 15 minutes from now, you would be able to tell what the system is. However, it's not the whole story, because the matter doesn't satisfy the Schrödinger equation. When the system is nice and small and uncluttered, then it seems to. When it gets too big in some technical sense, which I could say more about, but that's not everybody agrees on what that means. When it gets too big in some sense, then it doesn't follow the Schrödinger equation. Schrödinger got very upset about this, quite reasonably. What it does is that the wave function, that's what the Schrödinger equation is talking about, how the wave function evolves, and the wave function is describing the world according to the theory. There is a thing called the collapse of the wave function. So it doesn't follow the Schrödinger equation. And usually this is considered by when something or somebody makes a measurement. Now, in the old days, it was quite often thought of that a measurement or an observation, the word observation was often used, that suggests that some being comes along and looks at the system, and that's making an observation on the system, and that's the point at which you collapse the wave function. Probabilities come out, it's not a deterministic equation anymore, and it's a thing called the Born rule, which you have to adopt. Instead of the Schrödinger equation, you change your mind and say, okay, well, let's use the Born rule instead. And this changing of the mind used to be considered to be the effect of a conscious observer coming and looking at the system, looking in a sort of broad sense. Now, my view is quite different from that. It's almost the opposite. I'm saying that there is something out there in the physical world which at the outset doesn't have anything, at least not manifestly, to do with consciousness. It's the way that the world operates, and this happens to do with what happens when you try to combine quantum mechanics with that other great theory of 20th century physics, Einstein's general theory of relativity. Now, you see, there's a big school of thought which says, oh, well, we haven't brought them together yet. We need to quantize gravity. We need to bring gravity theory, Einstein's curved space theory of gravitation, you need to bring it within the scope of quantum mechanics. And that's the idea. Quantum mechanics is supposed to be the ultimate, which you bring, but without mentioning that theory is inconsistent with itself. Now, my view is the opposite, that to make it into a more powerful theory, which agrees more with the way when it doesn't follow the Schrödinger equation, what does it do? That's when gravity becomes important. And there are arguments one can bring to indicate this is quite plausible. That when gravity becomes too important in your system, then the state does not follow the Schrödinger equation, and it starts to jump in the way that the Born rule tells you. You get probabilities, you don't get a deterministic evolution. Now, I do believe that that's where we should aim for, and that's where, if you like, creativity will come in, because we don't have the theory yet. So it needs creativity to go beyond current theories of physics to introduce some new ideas which are indicated. You can see sort of aspects of the new scheme. It must have this effect and this. So you can see some things it's got to do, but we don't have the theory. Now, is that creativity? Well, it's creativity if it's not acting within the scheme that we had previously. Then you've got to be creative, because the theory we had previously doesn't give an answer here. It doesn't tell you what the collapse of the wave function is. It just says, you do it. And it doesn't say when. It just is a very incomplete picture. People like Einstein and Schrödinger and Dirac were a bit more polite than I am. They say the theory is incomplete. I'm saying the theory is actually self-inconsistent, so I'm a bit ruder than they were. But it needs something to be done, and that's where a bit of creativity absolutely is necessary.
We know of 4 different fundamental forces in physics. That's the electromagnetic force that most of you have probably heard of. Then we have the strong and weak nuclear force, and we have gravity. And the problem is that 3 of those forces, the electromagnetic and the 2 nuclear forces, have quantum properties. So we have some particles like electrons and quarks and gluons, stuff like this. And we know that they do funny things, like they obey the uncertainty principle, they can be in 2 places at the same time, that kind of weird stuff. And then there's gravity, which is described by Einstein's theory of general relativity. And that theory doesn't know anything about quantum properties. And this brings up the question, if I have a particle like an electron that can be in 2 places at the same time, and it has a mass, and that mass generates a gravitational pull, where does the gravitational pull go? You'd expect that to also go to 2 places at the same time. But Einstein's theory can't make that work, because it doesn't know anything about quantum properties. So this leaves us in this weird position where we just don't know what the gravitational pull of an electron is. So it's a really simple question, like what's going on with the gravitational field of this electron, and we don't know. And if you ask like more technically, what's the matter? It's just that those 2 theories, the quantum field theories that we use to describe particles, like the electron and a couple of other particles, Einstein's theory of general relativity, they're just mathematically incompatible. If we just put them together, it doesn't work. But nature knows how it works. So there's got to be a solution to this. And we don't know what it is. There have been many people who've tried to solve this problem. What we need is a theory of quantum gravity, so a theory that gives properties to gravity, at least that's the way that it's normally put, but more generally we need some way to resolve this discrepancy between the 2 theories. And the probably best known approach to this is string theory, that most of you will have heard of. There are other ideas like loop quantum gravity, and then there are less well-known ones like maybe asymptotically safe gravity and stuff like this. But so far, we don't know if any of those is correct or how we can even test them. And yes, I think it's a really big problem. Now, when it comes to my personal opinion on what to do, as I just said, like people have worked on this problem for a long time. It's been known since the 1930s or something, so it's definitely not a new thing. And there are lots of smart people have spent their whole life trying to fix something that they think is wrong with gravity. And I have a lot of respect for all those people, and if they couldn't make it work, I'm pretty sure I can't make it work either. So this is why I think it's a better strategy to try and figure out if not there's something wrong with the quantum side of things, that the problems may be caused by us not understanding what quantization means in the first place. I generally think it's not good to put our bets on one thing. So I'm really supportive of spending some time on modified gravity and different approaches to that kind of thing. Spending some time on the idea of trying to replace gravity or explain it as something emergent or induced gravity. This is a similar but related idea. Or maybe just saying maybe the fault is with the quantum side of things, which is what I personally work on.
Okay, so there we have 3 different approaches to this that you're outlining. Is the modified gravity as one way to go. There's this emergent picture of trying to reframe the idea of gravity to begin with, and then you have quantum gravity. So to the 3 debaters here, if you had to place your bets, Priya, on either of these? You say you're agnostic, but if you had to put some, if I gave you some chips now, you had to put them down on the table.
So what's the third option? So I think modifying gravity just with a view to adding additional degrees of freedom, but stay within the same framework where other cracks are opening up is clearly that's not where I would put my bet. But not little tweaks to the theory, but push it so that the cracks, to try to make sense of all these crises. So the modifying gravity so far has been really focused on the dark matter problem. So new, and I think as Sabine pointed out, new zoos of particles, right? Alternative particles. I think that's an approach that has been tried. A lot of energy has been spent, and I think it's been useful, it's taught us more, but that's not where I would put my bet on. The kind of pushing the theory that I'm talking about is actually trying to see these crises, going beyond just having a different kind of dark matter particle. I think that's where things are pushing us. Fundamentally look at the nature of dark energy and what we think dark energy is, for example. And then fundamentally looking at whether these conceptual ideas of dark matter and dark energy can somehow be, could they be two manifestations of the same thing? I think those kinds of ideas are totally worth exploring, and I think they should be, and not as much attention is being paid to them. We've been spending too much, so I would not bet on the modifying gravity. And I said with the quantum theory of gravity, I think that there's just like vast bits of things that we don't understand. So as a pragmatist, I would stick to sort of my view of really pushing the theory of general relativity with the view of finding a replacement theory for it. And I firmly believe that we will see new directions.
But Sabine, this approach to modified gravity, which has come to the fore a lot in the last 5 to 10 years, it's really gained a lot of interest and a lot of research in the field. I know you have also engaged a lot with that field. Do you see it, as Priya is suggesting here, more that it's limited kind of tinkering with the existing model, or do you think that there's a real promise in a kind of a breakthrough with understanding modified gravity?
Well, as you say, I've actually worked on modified gravity for a couple of years, and I used to think it's really promising, it's going to solve all these problems, and I don't work on it anymore because it turned out it doesn't work quite as well as I thought it would. It's like, from a theoretical side, it's really, really difficult to make those theories work. And I'm of two minds about this. On the one hand, they do have some really appealing properties where you can explain certain types of correlations that we observe, like as a matter of fact. We can explain them very easily. But on the theoretical side, they don't seem to work properly. So, and this, I'm afraid I actually agree with you. It just makes me feel like we're missing something really big. Like there's something fundamentally wrong with this type of theory because they don't work. With the mathematics doesn't work the way that we expect it to work.
Especially light deflection. I think one of the big, I was open-minded like Sabine. I dabbled a little less because, I'm invested in light detection, gravitational lensing. Those theories are unable to provide a description, and we see these lenses, we see these arcs. Hubble Space Telescope has shown us these arcs, right? So,
there are models which can explain that kind of thing, but then they have other problems. So it's like you're pushing around the bump under the carpet. It always comes up somewhere.
So Erik, where would you place your chips?
Well, someone said, don't modify gravity, but try to understand it.
Yeah.
And I think that's my approach. I want to understand gravity and then find answers. And maybe I should mention it here more clearly. There has been a lot of progress made in our field in understanding gravity. That comes from string theory. We have a theory that explains gravity microscopically. The only drawback is that it's not yet in a universe that looks like our own. It's namely one where there's no dark energy. That makes things a lot simpler. So the step that we need to make as theorists eventually is to develop this theory that we understand very well, but in a context where there is dark energy. And there I feel that we can indeed understand gravity to the level where we can do computations and make descriptions that clarify these observations, not by modifying it, but by really understanding what gravity is. To make clear, so I think it's starting from quantum mechanics and then deriving gravity again. And maybe I should mention that, Newton had a theory of gravity. Einstein didn't modify
Exactly.
the equation of Newton. He had a much better, much deeper understanding. So because he combined it with space and time and everything, a curvature of space and time, a totally new perspective. And I think our next theory of gravity will again not be a modification of the laws of Newton or the Einstein equations. No, it will be a totally new perspective that will be given on what gravity is.
The debate is not only between scientists and historians or philosophers. The debate is within theoretical physics. Yes, special relativity, even general relativity, has been proven in all kinds of experiments. But the collision between quantum mechanics and special and general relativity is being as sharper and sharper every day. And physics today, theoretical physics today, is still within a great controversy between these two, a great clash between these two theories. So here you have experiments in quantum mechanics which tell you that if two particles are being measured at the same time at different places, something, although not information, is going between them faster than the speed of light at infinite velocity. It's not information, but there is something. This is something which goes against special relativity, even general relativity. There is a problem here, but it's much worse. So many experiments in quantum mechanics tells you that when you make a measurement, you don't affect the particle in the sense that its future moments are being affected. You affect it also backwards, which means something really crazy. It means that it is not only that the future is open, but the past is not fixed, at least at the quantum level. We have papers on that. We have experiments which have been proved recently. I believe I showed such a paper. I presented such a paper in a conference which you were present. So we are at the verge of a huge revolution, which is at the magnitude of relativity and quantum mechanics at the beginning of the 20th century. There is something very important about scientists being humans, as Jimena says, but the schism is within theoretical physics itself. So many paradoxes which tell you that this picture, nice picture of 4 dimensions and all events being there, is far from being the truth. Let me just give one example and then I'll finish. A single photon hits a half-silvered mirror. You have 2 detectors here. I made some money with this. One of them is going to give you a click and the other is not going to give you a click. Nothing in physics can tell you. My scientific grandfather, David Bohm, was the father of, who was the advisor of Yakir Aharonov, believed in some hidden variables. There are no hidden variables. So here are 2 possible events in the future, which nothing in the present can tell you which of them will occur. That tells you that the future in some very profound way does not exist. Not only for you and Jimena and me. In some profound way, it does not exist, and it is being built. Our world is being built, our universe is adding an event after event in a way which is still a mystery to physics. But there is a lot of physics in it.
You were interviewed on a podcast, which the name of this podcast escapes me, but someone showed you a video of Eric Weinstein, who is criticizing not string theory, but string culture. And you said, hey, we welcome criticism. It's great. It's just that you should put something forward constructively rather than just criticize. And I believe the quote was put up or shut up. And I want to know, are you aware that Eric Weinstein has his own theory? So he has put up.
Well, so far, all the theories that have been put up that are rivals of string theory have failed. They failed for basically 3 reasons. First of all, the theory has to incorporate all of Einstein's theory, which they can do. Second of all, they have to accommodate the standard model. And that's where a lot of these theories fail. That means 36 quarks and antiquarks, 3 generations of identical subatomic particles, 20 free parameters. That's the standard model. Only string theory has the richness to describe the standard model. And third, which is the real killer, is that once you combine quantum mechanics with classical physics, you get anomalies, divergences, things blow up in your face. The only way we know to control these divergences is through supersymmetry, which is the symmetry of strings. In other words, string theory has no rival. I repeat, string theory has no rival. Other competing versions do not have the standard model or they diverge. Take a look, for example, at loop quantum gravity, which is a very interesting theory. I've looked at it. Loop quantum gravity has a problem. It has no electrons, which means it has no matter, which means it's a theory of pure space, which means it's kind of useless. It's a theory of pure space with no electrons, no standard model, none of that. And that's why string theory is different. String theory can accommodate the standard model.
Carlo Rovelli said that you can't have fermions in loop quantum gravity has only been true up until a few years ago. And that if anyone has kept up with the research in recent years, they'd see that they were able to produce it. And then also when it comes to string theory solving all of these problems, but other theories having issues, it's tricky to state that because there's also tens of thousands of people and plenty that go into string theory, whereas some other issues are just there in their bud. String theory in its bud also had issues that plagued it, and they were solved because plenty of attention and minds went into it. So you have to somehow normalize or reweight these theories by how much mental energy went into them. And if you do so, it's not clear to me, is string theory the winner? I don't know.
My attitude is let 1,000 flowers bloom. Let all of them bloom, mature, so that we can pit them against each other, okay? We're not going to hurt anyone's feelings. These theories have no feelings. So let them clash, and let's find out the limitations of these things. Loop quantum gravity has a problem with fermions. The fermion loops are divergent. They blow up in your face. The only way known to cancel these divergences is through supersymmetry, which is the symmetry of strings. So in other words, we're still back to ground zero. That loop quantum gravity does not have a theory with fermions that have finite results. And so what I'm saying is something very simple. You can read alternative versions that claim to have the theory of everything. Fine. But the acid test is to look for whether or not they can incorporate the standard model and whether or not they can control the divergences and anomalies. And so far, string theory is the only one which can do this. Now, that doesn't mean string theory is right. It just means it's the only game in town.
I wouldn't say that quantum computing is a hoax, but it is an extremely bold proposal. Right? It's the proposal that we can achieve something that nature hasn't done. That we're able to build something that is computing polynomially faster than any kind of classical process. If you look at the computers that we are building today, that we're using, if you look at our brains and all the interactions that we can observe in nature, they're all made of dynamics that we can describe as the interaction of particles or something equivalent. And quantum computing suggests that we can go below this level of the particle universe and tap directly into the CPU of the universe, and that the CPU of the universe is running much, much faster than the particle dynamics that we are seeing and that we are made of. Right? So it's an extremely bold proposal that is being made, and it's so complex that relatively few people actually understand its implications. And in the past, some of the people who saw the implications said there might be a possibility to basically bypass the particle universe with some arcane technology and build computers that are dramatically faster for some applications at least. And this is an extremely bold statement, and it consists of two parts. One is we can build a non-local machine, which has been built, right? You were involved in D-Wave. And the other one is hypercomputation. It's really it's about building something that is able to compute faster than a classical computer. And this might not be possible. But, or if it is possible, it might still not imply that the Church-Turing thesis, the computer science statement that all computers have basically the same power, just differ in memory that they have and processing speed. This will probably not be broken. Right? And there's the question, does quantum computing make the claim that it breaks this? Is quantum computing in part based on some faulty part of physics? Because the physicists have checked out the code base from the mathematicians before Gödel happened and before mathematics was forced to become constructive. So maybe there are some specifications in the mathematics that we use to describe quantum mechanics that give rise to hopes that we can build computers that cannot be built. And to me, it's very, very exciting to observe these developments because there are open metaphysical questions to be answered and whether this is being built. With respect to the practical implications of funding, a large amount of funding that was being made available as part of the stimulus packages during COVID and so on. And I found that when I talked to some of these companies, that the people in these companies did not actually understand how to build a quantum computer, which was very frightening to me. They did not understand the underlying physics. They were hoping that we have this physicist, our company, who's going to figure this out for us, but we are all building this amazing machine that's all going to make us rich if it ever works. Right? So it's a lot like crypto. And maybe this is enough as a start. My 3 minutes are over.
Well, I mean, for some of the theoretical sciences, such as physics, for example, this has been the driving mechanism for a long time, is this ideal of beauty that you refer to, and this idea that there should be an ultimate equation, there should be something that could somehow unify all the different phenomena that we know. And this is a very peculiar thing to physics, which is the only branch of science that I know that sort of submits the world to its own rational ideal. In physics, there's a long tradition for what can be called mathematical universalism, this idea that mathematical language can uncover the truth. The truth is out there to be discovered, and that scientists have the ability to do so. I think if you look at how the science has progressed, this is clearly not how it's actually working, but this ideal has somehow stuck with us that we can somehow uncover it. So that would be my first sort of objection to this way that we can find a single true account. Rather than thinking of it as true or not true, the different methods or the different theories and models can be useful insofar as they're convincing. So there's a battle going on all the time between scientists and people outside of sciences to convince each other that their idea is the right one. That is the battle. That's what a model can do. You can try to outmaneuver somebody else by trying to convince them that a model is true, or like has more hold or more sway. But this ultimate idea of the one model that explains it all, well, in physics, it's almost a century now looking for the single unifying theory. It's driving a lot of the discipline, a lot of the research and the funding and everything within the science is attempting to find the single correct view. But very clearly, we're at a point now where very few people believe in that anymore, that it is possible. That it's just the subject matter is too complex and overstretched to be able to find one true account.
Often, the starting point for thinking about matter and what it's made of is an equation. You don't need to understand any of these equations. Suffice to say that it has in it every electron interacting with every other electron interacting with every ion in the material. So you can tell if you have trillions of electrons, you have everyone interacting with every other one. One can write down an equation, but it's almost as complicated as literally writing down every single electron in the universe. It's not something one can readily solve. And even if one said, maybe one has a supercomputer, and maybe at some point it will be able to crunch this equation and give you an answer. Even if one were to say that, there's something else that happens that makes that very unlikely to give you the correct answer, and that's something known as emergence. So what is emergence? It's also something you might have heard in other areas, not just physics. It essentially relates to collective ensembles of objects collectively self-assembling to form something very, very different from the individual constituents. And you can think about people in crowds, so the collective behaves very differently from each individual member. You can think about something like consciousness. It would be very far-fetched to think of consciousness in terms of individual neurons, in cutting up the brain and saying, okay, What are the individual elements that make it up? And somehow I'm going to add them together and arrive at the functioning of the brain and consciousness. It's almost as absurd, it is as absurd to think about materials that are all around us that are made up of trillions of electrons and imagine that the collective self-organized processes that emerge from them, which are as complex and as exotic as consciousness, to be in some way derivable from a reduced equation of individual electrons. And this is just an example of one of the very exotic forms of emergent phenomena, which is superconductivity. So this is a superconducting material. The puck is a superconducting material. And this is a string of magnets. So essentially what you see happening here, you can see this is levitation. So superconducting materials have a couple of really interesting properties. Firstly, they conduct electricity perfectly without any loss. And this is a dramatic quantum property, and I'll show you an example in a bit. And the second is that they levitate. So if you put a magnet on top of a superconductor, it levitates. And this is quantum emergence in action. If you took a single electron or a few electrons, you would not get superconductivity. It would not be predicted from the model. The way superconductivity was discovered is that first people took materials, cooled them down to very, very low temperatures, discovered that they lost all resistance to the flow of electricity, that there was this amazing property of levitation. So it was an experimental discovery. And then they worked backward and said, okay, how can we form a model that now explains this?
Are you completely against the idea that we could, if we understood all of the constituent parts, say we had a complete knowledge of them, then we might be able to explain the emergent property in terms of its parts? Or do you think that they're always going to be missing something no matter how much we know about them?
I don't actually think that's a useful question, because at this point in time, right, we understand how two electrons interact with each other.
Right.
We don't even know how three electrons we struggle. In reality, in a milligram of material, there's 10 to the power 23 electrons. That's the number of stars in the observable universe. So I think it's a conceit, either for scientists or people talking about science, to talk about this idea of a theory of everything where we're at two particles. So we're not going to get to 10 to the power 23 particles, and the interaction between not just pairs of particles, 3 particles, 4, 10 to the power 23 particles. And even if we had such a theory, it would be reality, so there would be no point to such a theory.
Okay. Good. Well, that was my best question. It's not a useful one either, apparently. So let's go down the hill. Hilary, do you want to come back on something Suchitra said? Because you said, yes. That's true, I heard you a moment.
Well, I mean, I'd like to hear more about what you mean by encountering, but let me put that to one side. It seems to me that the idea that we have these, all of these bits, the electrons, and we've got a puzzle about how to describe the behavior of them as a whole, it is just the same sort of puzzle that I was describing initially. That it's the idea that maybe if we did have all of those bits, then we would explain the whole. And your thought that, well, we're not going to get there, so let's just engage in exploring how we encounter the emergent stuff, is still employing the notion that there are some bits at the level that we know about, electrons, and there is something more general. You haven't told us much about what the sort of overall behavior, what category you're going to use to describe that overall behavior. There is a problem of how you encounter it, is that you can't get from the smaller bits. So I'm not sure that there's really a difference, and that you're still relying on the notion that you've got the bits in the first place. So there is such a thing which is the electron, rather than an energy space, or however else we might describe it, and that you knew where you were, where your bedrock, you've got bits.
Actually, I'm not, right? Okay, I'll just be a little more specific as you asked for. Okay, so for instance, superconductivity is an emergent phenomenon, which you cannot describe in terms of individual electrons. Instead, you have trillions of electrons, the quantum behavior of which overlaps, and then you get this giant wave function, and that behaves completely differently to the individual electrons. So you do an experiment. By encounter, I mean you do an experiment, you discover something that behaves nothing like what we know of from individual bits. And then the theory that can be employed to describe it is a phenomenology, where we say we encounter this, and how can we describe it? And because we're only familiar with reductionist theories, we reduce it into a hypothetical particle. We don't start with the electron and make a theory to get to it, and we don't know that there will be such a theory. There might be an infinity of such theories, because yes, an electron would be a device if we went back to an electron. It's like, say there was the Escher progression, where you start with birds and you go to castles. If you see the castles at the end, that's superconductivity, you can't go back to the birds and say, how did you start with the birds and get to the castles? You could have started with oranges. You could have started with cattle. And the collective self-organization would have still given you the end product. So that's why I'm saying no, I'm not starting from that individual entity.
So I agree with that. But are you saying that the world is not differentiated then? Because I want to make the move and say the world's not differentiated. That's the consequence, the radical consequence of taking that through to all entities. Are you making that additional move?
I don't think the idea of there being an essential or an fundamental is a useful idea to even begin. So I wouldn't say it's differentiated. I would say, that's a nice project some people do, but does it tell us anything about the world? No.